Record. Today we're going to talk about independent events and look at the relationship between conditional probability and independence. Alright, so when we were drawing two cards with replacement, so I let somebody draw a card, the probability of getting an ace is 2 out of 5. I put the card back. That's what with replacement means. The probability of B, the next card being an ace, was still 2 out of 5. So when we use replacement, we say events A and B are independent. Which tells us that the occurrence of the first event has no effect on the chance that the other one will happen. So if we were still talking about the cards and we're still working with replacement, the probability that B is going to happen given A happened. So A is, I drew a card, it's an ace. I put it back in. The probability that B happens, I draw an ace, is 2 out of 5. So in other words, when events A and B are independent, the probability that B happens given A happens is the probability that B is going to happen whether or not A does. Because A has no effect on whether B happens or not. You can also rearrange it and say the probability that A happens given B happened is the same as the probability of A, because B has no effect on whether A happens or not. Those statements right here, this one and this one, if I ask on the test for you to let me know whether two events are independent, this is what you have to prove. That the conditional probability and the probability of the event happening are the same. And I'll show you that down below. Am I off the screen? Thanks, Bailey. Yeah. Do you know where my husband's classroom is? I'll let Michelle do it. She wanted to go to begin with. Thanks, Michelle. And thank you, Bailey. All right. Probability of A and B. I taught you guys the general multiplication rule yesterday, how to find this. Multiplication, I'm going to abbreviate. I just can't, my handwriting's too big. So yesterday, I taught you the general multiplication rule that the probability of A and B is found by taking the probability of B given A and multiplying it by the probability of A. Well, we can simplify that if our two events are independent. So when we have independent events, the probability of B given A happens is the same as the probability of B. So we have a multiplication rule for independent events that says we just take the probability of B times the probability of A. And I should have labeled this, sorry. This is the multiplication rule for independent events. Just like with our addition rule for mutually exclusive events, we can use the general multiplication rule, because if B and A are independent, the probability of B given A happened really is the same as the probability of B. So if you don't want to memorize an extra rule, this one will work for independent events. But they do simplify it for independent events and say we're just taking the probability of B times the probability of A. Questions? Well, hopefully when I put it into a situational context down below, it'll make more sense. All right, so down below, we're going to determine whether the events are independent. And that means that we're going to prove what I said up here, that the probability of B given A is the same as the probability of B. Or, because I can't remember which ones we're actually showing, A given B is the same as the probability of A. I know these use A and B, and I just can't remember which order we're showing. So on number 1, it says we're going to shuffle a standard deck of cards and turn over the top card. And we're going to put it back in the deck, shuffle again, and turn over the top card. So event A is that the first card is a heart, and event B is that the second card is a heart. So we're going to go with P. We want to show that the probability of B given A happened is the same as the probability of B. We're going to pretend I shuffled, okay? So we're going to, we have a deck of cards, I shuffled them, and we're going to turn over the top card. Event A is the first card is a heart. So I got a heart. So A happened. Then following the instructions, I put it back in the deck, shuffle again, turn over the top card, and we want to know the probability that we get a heart given that A happened. So what's the probability I'm going to get a heart? What? How many hearts are in the deck, and how many cards? There aren't 26 hearts. 13 hearts. And how many cards are in the deck? 52. Now, what's the probability of B by itself? So I flip, of course, I somehow have a heart on top. And I have another heart. Seriously? All right. There we go. So I shuffle, I flip a card over. A didn't happen. Okay? I put the card back in, I shuffle, and I flip another card over. So A didn't happen. What's the probability that B is going to happen? 13 out of 52. So did the fact that A happened change the probability that B is going to happen?
No.
No. So A and B are independent in this case. Therefore, three dots mean therefore. Sorry, I thought I had used that one before.
So
And
if it's the hearts, do you not count all the rest of
my events have to do with the card being a heart, so I don't worry about spades, clubs, or diamonds. Alex?
Could you use a deck of cards to test if you have problems with stuff?
That's a new question.
It'll help me out.
I have like 10 deck of cards over here. So if you need a deck of cards during the test, you can come borrow one. Any other questions? Michelle?
I mean, if we like forget, say like how many hearts or spades are in a deck, can we just ask them to tell us, or is that like a guess?
So I will tell you.
Oh.
The only thing is you need to know what's in a deck of cards if you're taking the AP exam, because they will throw deck of card questions on there and they assume everybody knows what's in a deck of cards. And I have to say, every year I'm always surprised how many kids don't know what's in a deck of cards. So
I'm not always sure if
I guess I grew up playing poker a lot with my parents, so I know what's in a deck of cards really well. I will be honest though, I don't play poker with my kids, so they probably won't know what's in a deck of cards as well. But if you have a question you can't remember, I'll try to have you think through it based on what you do know about a deck of cards. But if you get to the point in May that you're taking the AP exam, they're going to assume you know what's in a deck of cards. Any other questions before we look at number 2? All right, did somebody say wait? Anna?
So, like, they just don't affect each other. That's because, like, when we did the one-up, obviously, like, if you don't pull it out, it doesn't affect it, but when you do pull it out, it does. So, it doesn't matter that it's the same.
Right, that statement I highlighted is what pretty much tells us we're working with replacement. Told me to put the card back.
Okay.
So it's not going to affect it. On 2, same idea. We're going to shuffle our deck of cards, flip the top 2 cards over, one at a time. Event A is the first card is a heart, and event B is the second card is a heart. So we want to show that B given A is the same as the probability of just B. So here's my deck of cards. I shuffled. I flip over my top card. Event A happened. So what's the probability that this next card is a heart? 12 out of 51. I only have 12 hearts left in the deck, and I only have 51 left. Okay, so then the probability of B happens. So I flip my first one. It's a club. So A did not happen. What's the probability B is going to happen? 13 out of 51. There are 13 hearts left in here. There's only 51 cards, Anna.
But the first card you flipped over was a heart, wasn't it?
So that was to talk through this probability. I flipped over a heart. What's the probability B? I get another heart is going to happen. Well, that means there's 12 hearts left out of
Okay.
51 cards.
That makes sense.
Then for B, without A happening, I still have to flip a card, but it's not a heart. So then what's the probability B happens? 13 out of 51. They're not the same. So in this case, A and B are not independent.
Wait, this 13 out of 15.
Say that again, Alex.
Just 13 out of 15 equal 12 out of 51. That's what
All right. You guys are going to try number 3. You're trying to prove independence or not between the events being female and right-handed for this set of data. On this one, it doesn't matter. You can see if probability of being female given that right-handed is the same as female, or you do right-handed given female is the same as right-handed. Doesn't matter which one you do is the given on this one, since there's no order. On the others, it's at first card, second card, so the order matters, but this one it doesn't. Oh, I knew that. It took a minute for my brain to catch up. I'm tired. Yes. Noah gave somebody a concussion, or Noah got a concussion.
Did he give something? Like last year.
Why would you do that? That's why I don't like wrestling. It's unhealthy, the way they make you cut weight, it's just not.
Is it 18 out of 28?
Yeah, if there's replacement, it will specify replacement.
So like, I'm confused. Isn't the probability of getting a female right-handed added over class 18 out of 29?
Say that again.
Because this question is asking if events of interest are getting a classmate or a person or a student from the class that's female and right-handed. And isn't that the probability?
I'm asking you to show me whether female and right-handedness are independent. I'm assuming that female given her right-handed. So your total should be out of right-handed.
So I should only use 21? No, yeah, I'm 21.
Oh, we're looking to see.
But then for all of them,
It's 21 out of 20.
when I still
Except for your confusion.
What I did it down.
18 out of 24 simplifies by.
Wait, think about it.
Is this part good? This?
No.
Well, yeah, pretty sure equals.
Ah, yeah.
Is this one?
Let's go.
Oh.
What'd you get? They are.
And then tell me if they're equal or
Oh
not.
my gosh, I told you what it was.
How many right-handed people are there?
Huh?
This is females given their right-handed, so it should be on the right-handed. No, not that one. This one. Okay.
So this is given to
Two fractions, not simplified.
So you take the two or the other right now.
I think you do.
We would do it on the right. Yeah. You guys just saw the numbers weren't perfectly equal. Alright, Chili. Probability doesn't like you. Alright, Jillian's putting one way on board that you can do it. Cheyenne. You did right-handed given a female, correct? We use social yeah. Please and people. Yeah. Because kids are getting hung up on that part. Thank you, Jillian. Alright, so she did female given right-handedness and compared it to the probability of female, which, walking around, most of you chose this order. I saw a lot of you that had 18 out of 28 for this one. Okay, you're looking at female given they're right-handed. There are only 24 right-handed kids in class. So if you're looking at right-handed as your given, you should be using the total of the right-handed kids. And then females, there's 18 out of those 24 who are female. I did see some of you who had this, and then you said they weren't independent. Fraction simplified, so either simplify it to 3/4 or actually use your calculator to divide and see if the decimals are the same. Cheyenne did it, she did right-handed given female, so I'm going to have her compare hers up on the board, just so if somebody else did it, that way you can see. Hold up. What's 24 divided by 28?
24 divided by 28. Oh. What is it? Oh wait, sorry, it's not 1/2, sorry.
That's okay.
Okay, so they are.
Thank you.
Thank you.
All right. So either way, you get that they're equal. So it doesn't matter whether you did female given right-handed or right-handed given female. Any questions? Right. So, let's look at this one. So here we have a two-way table that shows whether a person graduated high school or not and whether they're a homeowner or not. So we have high school graduate and not a high school graduate going across the top, and then our total column. And then we have homeowner and not a homeowner, and then the totals on the bottom. So what is the probability that a randomly chosen person is a high school graduate? 310 divided by what? I'm sorry. Thank you, Hannah. 310 divided by 500. High school graduate total 310, grand total 500. I was going to try and do that in my head, but my brain is not quite on. 0.62. So if we know that a person owns a home, so there's a given condition, what's the probability that the person is a high school graduate? So we want to find the probability that they graduated from high school given they own their home. So how many people own their home? Our given condition, how many are homeowners? Homeowners only 340. And of those homeowners, how many graduated from high school? 221. And I definitely don't know that on top of my head. 0.65. What did you say, Zach? Oh, okay. So what do the answers from 1 and 2 tell us? That our two events, being a high school graduate and owning a home, are not independent. And then part 4, if we know that the person's a high school graduate, what's the probability they own their home? So this time, the given is they're a high school graduate. So this time it's home given they graduated from high school. So how many of our numbers graduated from high school? Total high school graduates, 310. And of those 310, how many own their home? 221. So this time we get 0.71. How come these two don't give me the same answer?
Because you're dividing different sections.
A lot of kids confuse that they should be the same. They're not, because the given is different. So like Hannah said, my denominator, divisor. Is it the divisor or the dividend? Doesn't matter. The denominator is different because I have a different given condition. But I do see often that kids think that they should just end up being the same, but they're not. All right, now I'm going to ask you to really rack your brain. And we're going to go all the way back to the very first day of this unit. Carter shook his head. He said, not happening. Can I move the paper up?
Yeah.
Okay, so on that very first day of the unit, we did the Mountain Dew simulation where we rolled a dice and we said 1 in 6 is a winner. If we buy an 8-pack, what's the probability that we don't have a winner in an 8-pack, right? So we're going to go back to that idea and we're going to find some probabilities. So Mountain Dew says the probability of winning for each bottle is 1 in 6. We are going to assume each bottle is independent, meaning when I open my first bottle of Mountain Dew, if it's a winner, it has no effect on whether the next bottle of Mountain Dew is a winner or not. Or if I open it and it's a loser, it has no effect on whether the next bottle is a winner or not. Instead of buying an 8-pack this time, we're going to buy 5 bottles. We want to figure out the probability that he wins on all 5 bottles. So since we assume independence, we flip back. The multiplication rule for independent events is the probability of B times the probability of A. So we're going to find the probability that all 5 win using that rule. So I have a bottle of Mountain Dew. What's the probability this one is a winner? 1 out of 6. Next Mountain Dew bottle, what's the probability it's a winner? 1 out of 6. Next one, what's the probability it's a winner? Next one. And the last one. So, a lot of times with independent events, if the probability is the same every time, they'll simplify it down and say it's 1/6 to the 5th power. Which 1/6 to the 5th. You guys know how to read that, right? I feel like I've talked about it in this class before. Scientific notation, since it's got a negative after the E, I'm going to move my decimal to the left 4. If it was a positive number after the E, the decimal would move, I can't speak, would move to the right. So I got 1.286 times 10 to the negative 4. So I'm going to move this guy to the right. Seriously. Left 4. 1, 2, 3, 4. So I'm going to have 0.0, 1, 2, 3 zeros.
There we go.
Any questions? All right, now this one, I think it should be a rule of probability, but it's not. It shows up a lot, at least for how many probability type questions are on the AP exam. I see these at least 1 questions quite often. And it's not its own rule, but I think it should be. So we want to find the probability that he wins on at least one bottle. What does at least mean? I think it was Michelle. You're so quiet over there. You said more than one, right? Yeah, means more than one. So he could win on one bottle, or he could win on 2, or 3, or 4, or all 5, right? So we'd have to find the probability that we have one winner. And then we would have to add it to the probability we have 2 winners. And we'd have to add it to the probability of 3 and 4. And then the probability that all 5 win. Now, this one, it wouldn't be a huge amount of work to do. But sometimes it'll be that you have 100 bottles. And what's the probability you win on at least one of them? And that's way too many things to do. So this is where I think it should be its own rule. The probability that you win on at least one is everything except for the probability that none of them win. So it's a complement rule. Another way to phrase it is the probability that all lose. Now the problem tells me the probability that a bottle is a winner. So what's the probability that a bottle is a loser? 1 in 6 is a winner.
5 out of 6.
5 out of 6. And if I'm going to lose on 5 independent bottles, I'm going to do 1 minus the probability that I lose on all 5. So 5 sixths to the 5th, and then 1 minus that, we get 0.598. So the probability that he's going to win on at least one bottle is 0.598. Questions? So if the AP exam, like I said, this at least one idea shows up quite often, you can promise I'm going to put it on my test. Yeah.
So since he bought 5 ones,
Mhm.
we just have a possibility he doesn't win.
So winning on at least one means he could have 1 out of 5 winners, 2 out of 5 winners, 3 out of 5 winners, 4 out of 5 winners, or 5 out of 5 winners. So the only thing that we're not covering is that he has 0 out of 5 winners. So it's a lot easier to figure out the 0 out of 5 probability than it is to do a bunch of probabilities and add them together. Because a lot of times it won't be 5, it'll be like 100. It'll say, what's the probability at least 1 out of 100 people win? Something like that. And you don't want to have to find 100 different probabilities and add them together, so you do the one that's not covered in the at least statement. Zach?
Is that 0.598 the non-win or?
No, that's the probability that at least one of them is a winner.
So if you were to answer that, you would say like the probability that he wins at least $1.598.
Uh-huh.
Okay.
Any other questions before we flip to the next page? Yes.
How many questions do you think we're gonna list?
10 multiple choice, 5 short answer, 2 free response.
It's always gonna be 17.
Yep. All right, baseball. In baseball, a perfect game is when a pitcher doesn't, should say allow, sorry. Allow any hitters to reach base in all 9 innings. Historically, pitchers throw a perfect inning, which is an inning where no hitters reach base, about 40% of the time. So to throw a perfect game, a pitcher needs to have 9 perfect innings in a row. So what's the probability that a pitcher throws 9 perfect innings in a row, assuming the pitcher's performance in an inning is independent of his performance in other innings? That was too many in sounds. We have independence. Tells us it's independent. And we want to know what's the probability that they throw 9 perfect innings in a row. So what's the probability of throwing a perfect inning? 40%. So the probability that first inning is perfect is 0.4. What's the probability the next inning is perfect? And the next. And the next. And the next. For 9 innings, right? So rather than writing 0.4 out times itself 9 times, we're just going to do 0.4 to the 9th power. Ah, there's that E with the negative thing again. 1, 2, 3. 1, 2, 3, 2, 6, 2. So the probability of a perfect game is really small. Really, really small. And it's really boring. It's 2 people playing catch. It's what a perfect game is. What kind of sport calls that perfect, where only 2 people get to play out of 22? It just doesn't make sense. Any questions? No? All right. Here's another one of the at least questions. The first trimester screen is a non-invasive test given during the first trimester of pregnancy to determine if there are specific chromosomal abnormalities in the fetus. According to a study published in the New England Journal of Medicine in November 2005, approximately 5% of normal pregnancies will receive a positive result. If 100 women with normal pregnancies are tested with the first trimester screen, what's the probability that at least 1 woman will receive a positive result? So here's, excuse me, that idea. At least one of them gets a positive result. That could be 1 out of 100, 2 out of 100, 3 out of 100, all the way to 100 out of 100. And we'd have to add all those together, and that's just too much work. So what we do instead is we say, okay, what would be 1 minus the probability that none of them get a positive result?
95%.
Well, that would be the probability that we get a false, which is part of doing this problem correct. So we want to find When I say none of them get a positive, that's the probability they all get false on their test. And we are given the probability of getting a positive result. Is 0.05. So like you said, Alex, the probability of getting a false or negative, I guess would have been the better word there, is 0.95. Now I want all 100 women to get that false or negative result. So I'm going to do 1 minus 0.95 to the 100th power, because I need all 100 women to get that false or negative result. So 0.95 to the 100 power is that, and then I'm going to do 1 minus that. So the probability that at least one out of those 100 women with normal pregnancies gets a positive result is 0.994.
That's it.
Questions? All right, last thing that I'm going to talk about. In years past, I've noticed that kids tend to get confused about mutually exclusive and independence. Mutually exclusive, remember, means two things cannot happen at the same time. Independence means that the first event happening has no effect on the next event happening. So what we're going to do here is we're going to read through these and we're going to determine if the events are mutually exclusive, independent, both, or neither. And just as a reminder, mutually exclusive is what I mean by ME. So working with our standard deck of cards, event A, the card is red, and event B, the card is a club. So let's start with mutually exclusive. Can I have a red club? No. Clubs are black. Where to put my deck of cards? Say that again? Diamonds and hearts are red. So there's 3 of the suits. There's 4th suit. So hearts and diamonds are red. Clubs and spades are black. So event A is my card is red. Event B, my card is a club, which is that one. So I can never have a red club. So A and B are mutually exclusive.
Because they can have bands.
Correct. Then we have to think about independence. So probability of B given A, and we want to see if it's the same as B. So A happened. My card is red. How many red cards are there?
26.
26. So given that my card is red, there's 26 cards total. What's the probability, or how many of them are a club?
13.
No, 0.
Oh, yeah.
There are 0 clubs that are red cards.
I thought you were talking just about club, not my bad.
You're fine. And then the probability of B, how many clubs? 13 out of? Are these the same?
No.
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 So A and B are not independent. So in this case, they were mutually exclusive, but not independent. And I'm going to abbreviate independent. Any questions on that one? So the next one, still picking a card from our standard deck. Event A, the card is red. Event B, the card is a 7. Can I have a red 7? Yes. So in this case, A and B are not mutually exclusive. And then we want to check independence. So given A, my card is red. That means I'm working out at 26 cards total. How many of those red cards are 7s?
No.
2. And then just my card is a 7. So how many 7s? 4 out of, are those the same? Yes, they both simplify to 1/13. Or if you want to check the decimals, they are the same. So in this case, A and B are independent. Not mutually exclusive, but independent. Last one, still working with the deck of cards. A, the card is red, and B, the card is a heart. Are they mutually exclusive? No, because all hearts are red. And then we're going to check our independence. So given my card is red, means I'm working with 26. How many of those red cards are hearts? 13. Oops, I wrote A here, sorry. That should be B. And then just the probability my card is a heart. I have 13 hearts out of how many cards total? Are those the same?
No.
So in this case, they are not mutually exclusive and they are not independent. Just to give you a heads up, because I don't see it tomorrow. So you have your homework tonight. It's just 5 problems. So even if you have a 5-hour choir concert, sorry Nate, I get the 5-hour choir concert being why you didn't get your homework done. And then because that first day we didn't finish, I think I told you yesterday we're going to get rid of one of these review days, and your test still will be next Tuesday. Okay, so don't expect next week to come and have 2 days of review. I don't want to wait until Thursday to start your test. I want to start it on Tuesday. Any questions? None.
Is the test going on before?
Yes.
Yes.
Yes, that's my plan. I mean, we do have a 4-hour meeting on that Friday in the morning before we're allowed to sit and do our grading. So,
4 hours?
yeah.
Why?
Really.
Oh, what?
That's a great question. In my opinion, it's about, hold on, let me stop recording.